fusion, and that indeed works. There's just one problem. At least so far, hot fusion eats up far more energy than it releases. We talked about the problems with hot nuclear fusion in this earlier video. But nuclear fusion is possible at far lower energy, and then it's called cold fusion. The reason this works is that atomic nuclei don't normally float around alone, but have electrons sitting in shells around the nucleus. These electrons shield the positive charges of the nuclei from each other, and that makes it easier for the nuclei to approach each other. There's just one problem. If the atoms float around freely, the electron shells are really large compared to the size of the nucleus. If you bring these nuclei close together, then their electron shells will be much farther apart than the nuclei, so the electron shells don't help with the fusion if the nuclei just float around. One thing you can do is strip off the electrons and replace them with muons. Muons are basically heavier versions of electrons, and since they are heavier, their shells are closer to the nucleus. This shields the electric fields of the nuclei better from each other and makes nuclear fusion easier. It's called muon-catalyzed fusion. Muon-catalyzed fusion was theoretically predicted already in the 1940s and successfully done in experiments in the 1950s. It's cold fusion that actually works. There's just one problem. Muons are unstable. They must be produced with particle accelerators, and those take up a lot of energy. The muons then get mostly lost in the first fusion reactions, so you can't reuse them. There's a lot more to say about muon-catalyzed fusion, but we'll save this for another time. There's another type of cold fusion that we know works, which is actually a method for neutron production. For this, you send a beam of deuterium ions into a metal, for example, titanium. Deuterium is a heavy isotope of hydrogen. Its nucleus is a proton with one neutron. At first, the beam just deposits